Okay, good morning, class. Okay, welcome back to the second week. Okay, let's get started. I have done a little bit of review in the first lecture. We also introduced the course content, expectations for this course in the first lecture. Before I formally start my second lecture, I just want to have finished that example. I didn't quite finish, just very little bit to finish there, okay? Essentially, it's a review on computing integrals, and this is a very common technique. So, just a second here. So this part I call it substitution rule. You probably will end up using substitution rule in quite many examples here. So what I have introduced to you is the formal substitution rule, what you have learned in your class. Okay, so this is what you learn in the class. Is very straightforward. But in my lecture, you probably see the way I solve this sort of integral. Okay? It may be not as traditional as you have seen in your previous lecture. So what I do typically is, instead of I introduce a u for 2 theta over plus 3, so what I strive to do is, I strive to make the theta here, okay, to be the same as 2 theta plus 3. So essentially, I'll write it down and I'll see a little bit why. So I'm changing the theta to d2 theta plus 3. And as I introduced in the first lecture, d is called a differential operator, right? So differential operator. So when you put a d and then there's a bracket, and you can put any functions within the bracket. And you can put as simple as x or simple as x squared, right? So anything in the bracket. So in my case, we have a 2 theta plus 3, right? So the differential operator function is similar to the derivative operator. So d2 theta gives you 2d theta. Right? So that 2 is a constant, the coefficients taking out of the d. And a d constant is 0. So this term here basically ends up with a 2d theta. Right? So this term here is 2d theta, but I don't have a 2, right, in the previous step. So what do I have to do? And I have just divided by 2, right, to make sure the steps are consistent with each other. There's no change, right, in the expression. So that's the way of a substitution, more or less the same as substitution. But by the way of doing this now, both of these variables inside the bracket for cosine and the quantity inside the bracket for the d becomes the same. Essentially, it's like a cosine u du, right? It's the same variable now. So now you can treat 2 theta plus 3 as one single entity, and then you integrate cosine. Cosine u du is what? The sine u, right? So you end up with just 1/2 sine 2 theta plus 3. So that's the probably what you will see in my lecture. Sometimes I write for simple substitutions. I'll solve the problem using this approach here. Now, what's the advantage? You might say, what's the advantage doing this? The advantage of doing this is you save yourself a step of this. So in the traditional substitution, you let the u equal to something. When you convert a u at the end, you have to substitute the new integral limits, right, based on the u variable. But in this case here, I don't have any u at here, and I have a 2 theta plus 3. If original is a to b, right, it is still a to b. So there's no change in terms of integral limits. So save yourself a little bit of potential to make a mistake, right, when you try to convert the limits to new numbers. That's the only advantage here. Other than that, really, there's no difference at all. Right? So it's up to you. I just want to make sure that we're on the same page. If you see what I write here, don't confuse. Did I learn that, right? If you're not comfortable with this, that's fine. You can just use your traditional substitution technique. Absolutely okay. Okay? Yeah. All right, so let's continue a little bit, a review, and then I'll get on to the topic of introduction to signals and systems. So the last part of the review I wanted to do is, okay, this might be new, okay, but may not be new. Okay, let's see. So the part is I want to see is how do we graphically add, subtract, or multiply two functions? Because the first, after the today, maybe on Tuesday or next week, we're going to start the convolution concept. We will use graphic approach to solve the convolution. So in that case, you need to be comfortable with how to graphically manipulate the multiplication or subtraction or addition of two graphs. For some graphs, it's pretty straightforward, okay? But I'm going to specifically pick maybe two particular graph right here. Okay? So let's say first graph is this one here. I call it f of 1 of t. And this graph looks like this. I use the red color to graph this. So this is f of t here. To label it properly, it's a rectangular box. Not very much like an exponential decay function or sinusoidal function. Right? It's a rectangular box type of function because it looks like a rectangle here. And then I'll say a little bit more. Let me draw the second graph. So that's the second one, f2 of t. So let me explain a little bit what the rectangle box at here is. Okay. So I draw the red one representing this function over the traditional function t coordinate system. Okay. So as you can see, if this is negative infinite, as t go from negative infinite up to 0, the value of this function is always 0. And then at the t equal to 0 point, there is a 90-degree jump and reach at 2. Okay. And then from 0 to 2, you have a value of 2 for this function. At the t equal to 2, it jumped back to 0. And then all the way to positive infinite location. So that's basically what f of 1 of t is. So sometime later we're going to learn a so-called a unit step function. So we'll see how we can actually use that function to describe this one. So this one is, we call it it's a step. It's a step up. Right? There's a step up right here. And this one, very much similar to f1 of t, except the value here, right, at the t equal to 0, jump to 1. And it only lasts for 1 second, or if this is seconds. Right? And it kept it as constant of 1, and then come back to 0, right, for f2 of t. Okay? So that's basically what f1 of t and f2 of t, what they are when you see these kind of rectangle boxes. Good? Okay. So now my point here is, right, is how do we, let's say, add these two functions together? And how do we let's use f2 of t. Subtract the two functions from each other. Okay? Okay, so I want you, especially at this stage, if this seems new, I want you to follow the steps, okay, closely. Once you become comfortable, you can certainly neglect a few steps here, okay? When you do this kind of a function, adding or subtracting for each other graphically, the first step is you sketch both graphs in the same coordinate system or in the same time history graphing. So essentially, you draw a new function and time axis, so that you can label. You don't have to label, but basically now you're going to draw both of them in the same system, right? So when you draw both of them in the same system, and make sure you draw them not precisely, but down to the accurate level. Okay? So up to the maybe similar scale. So for example, if this is a 2 here, this is 2 here, and this is a 1 here, right? So they need to be in the same range. So if I draw f1 of t, I'm going to use the red color to draw f1 of t. There. So that's f1 of t. If you want to be very sure, you could always, right, just basically add an arrow here, make sure you know this is f2 of t. Sorry, what did I label here? This is f1 of t. I should say, right, this is f1, that's minus f2. Right? So f1 minus f2. So label this as f1 of t. And then you draw f2 of t, which is this one here. So that, let me use a black color now. Right. So the black one is f2 of t. So this way, it's not very accurate, but it's fairly a good depiction of what they are, right? Yeah. So this is 1 here. Label the important values, okay, appropriately on this graph. So once you've done this, and then you can start working on the subtraction or addition. So let's work on the addition first, and then you can practice subtraction yourself. So if I need to add the two graphs together, right, so then how do we add them graphically? So if I don't ask you to add graphically, if I ask you to add what's 1 plus 2, okay, so that's 3, right? What's 2 plus 3? It's 5. So that everybody knows that. But the problem here is we're not adding just 2 numbers, right? We're adding so many numbers at t equal to different range, different value. So basically, when you add 2 functions together, what you're adding is, what is the value at the t equal to 1? What is the value at t equal to 2? What is the value at t equal to 3? You add all the infinite, basically, number values for t, and you plot them out, and you get the addition of the two functions, the addition of the functions, right? So graphically, what you do is, you can actually look at the chunk of the graph here. So for example, right, at t less than 0, when t is less than 0, this is 0 here. When t is less than 0, both of the function, the value are what? Both of the functions' value when t is less than 0 are 0, right? So when you pick any locations, okay, on the left side of this t equal to 0, both of them 0. And when you add a 2 0 together, you get a 0, right? So if this is 0 here for anywhere on the left side, and you get a 0, right, when you add them together. And now, slowly inching into the meaningful range. And in this part, most probably you're going to have to do it piece by piece, so piecewise. Right? Don't jump too far. So let's say starting from 0 up to 1. So you look at this one here, between 0 and 1, this f1 of t value is always 1. And between 0 and 1, the f2 value is always 2. So if you pick any point, any location, right, any location between 0 and 1, you'll end up with adding what and what? 2 and 1, right? So between 0 and 1, when you add these together, you get 3. So let me put the 1 over here. That's exactly what happened when you move your t value, right? Slowly to your right. Between 0 and 1, you end up with 3. And then between 1 and then 2, the f1 value f2 value goes to 0. But f1 value is still kept at 2. So between 1 and 2, you end up adding 2 plus 0, which is 2. So that's 2 over here. Right? So you're stepped down by a value of 1 from 3 to 2. And after the t equal to 2, both of the functions go back to 0. So you end up basically with a 0 for the rest of the value. So that's the results of the addition of the two graphs. You got to step down, you got to step up, and then step down, right, like this. So the key here is, as you can see, you don't go too far. You go slowly, right? You go a little bit, until usually things happens at those so-called edges, right, or the critical values. Okay, there's a bit of a step change, basically. Okay, any question on this? Graphing, graphical adding the two functions? Okay, good. Okay, so I want you to practice yourself. Okay, so then essentially, I should probably write here. Let's say step 2, right? I should say this is step 2. Now the other thing, step 2, I also need to emphasize is when you draw this, the coordinate system and here, I want you to draw it on top of each other. Okay, so basically they're aligned with each other. So then you can even use a ruler to find out the critical edges. Okay, what happens at the critical edges? So this is essentially the two graphs sit here. They are on top of each other. So you have a better view and better alignment of the values. Okay, I'll give you a few, maybe 1 or 2 minutes here, just to try out what is f1 of t minus f2 of t. So if you want to use your ruler, absolutely fine, to make it much more accurate. Again, you draw the new system on the bottom, right on the bottom of the original graph f1 of t and f2 of t. Okay. And then you try to do the subtraction by changing the t value from the left to the right, from negative infinite to positive infinite. So the red subtract the black. If you do it fast, you can probably finish within 15 seconds. But take your time at the beginning, right, to completely understand how to graphically add or subtract or even multiply two functions. Okay, let me see your hand who has finished, completed. Okay, the timing is good. Excellent, good, yeah. So I'll just draw it here, and you can verify, see if we're on the same page. I'll use the red color again for the end results. Again, when t is less than 0, everything's 0, so subtraction end up with 0. Between 0 and 1, you end up with a number 2 minus 1, which is 1. Okay, so that's 1 under here. And that's up to 1. So essentially, technically, they all should line up, right? They all should line up here. And between 1 and 2, you end up with a 2 minus 0, and that's 2. So in this case, you actually end up with a jump at between 1 and 2 for t's value. And after 2, things go back to 0. Right. So you got to now you got to step up, right? Yeah. A stared up signal. Let me see. Did you get it all right? Raise your hands. Okay, good. That's very good for initial try. Excellent. Okay. So the key, as I mentioned, is to do it slowly and do it piecewise. Try to observe the critical or the edges, okay, based on the given functions, and then you draw it properly. Okay. I also emphasize, in my even if we mark assignments, okay, at this stage, you should always label your x-axis appropriately. If this is a t, you label as a t. If this is x, then you label as x, right? And same thing, the vertical axis should also be labeled, representing the functions you have just generated. So this basically gives everybody a clear picture of what you have drawn and what you're presenting at here. Okay, good. We'll have a little more opportunity to practice graphically adding and subtracting or even multiply functions. So maybe you can also try what is the multiplication of the two functions yourself. You can try it. Right. You follow exactly the same approach and see what happens, right? Yeah. Okay. So now I'm going, that's pretty much the review I wanted to do. And now let's go into the actual content of this course. So the first part, I want to say a little bit about the concepts of signals and systems. So as I said, this course in the first lecture is a little bit of mixture of signal systems, then plus solving linear differential equations, okay, linear ordinary differential equation more specifically. In a traditional math course, they don't really cover this part, the signals, the systems. Okay. So this is more of engineering curriculum-wise for you to be ready for the next stage of your electrical or mechanical or possibly some area in civil. Yeah. So first, let's talk about the system concept. Okay. I think I mentioned this a little bit already in the first lecture, is that when we talk about the system, we can always use a box to represent a system. And that's very common to see, especially when you design a control system, you draw a box to represent an actual system. The box can be anything inside. A typical system is that you have one input, and then you have one output. So we call it input signal, and then you have another one, we call it output signal. Right? So input signal, you let it go into the system. And then you have maybe a certain type of a scope you can measure at the output location terminal, and you get the so-called output signal. Right? So we call this is a single input and the single output SISO system. When you start learning control system, or when you start learning the basic concept, we usually will start with single SISO system. Of course, more realistic system or more complicated system, right? You can certainly have more signal inputs. So now we call it input signals. Right? So there are more inputs to the system. And then you can certainly have more outputs. So now we call it output signals. In reality, this is certainly the most typical type of systems. So we call this as a multi-input and then multi-outputs. We call it MIMO, so MIMO. Okay, that's the bigger picture. Okay, without getting into the detail, there certainly you can see there are more advanced level modeling to study the dynamic system, right, for multi-input, multi-output system. In this class, we'll focus on the SISO system. Okay, so now let's come back to the more of the definition. Let's look at, so we listed the signal, we listed the system here. What would be a better definition for signal and system? So first, let's look at the signal here. Okay, so if you look into the Webster dictionary, if you look into some other dictionaries, you probably will see a different type of definition. But the following is more of my interpretation of signal and systems. Okay? Yeah. People in the back, can you stop chit-chatting? Okay. Good. I guess if I could hear you, I'm sure your classmate could hear you too. Okay? So when we talk about signal, my definition would be, okay, it's a type of energy. Okay? It's energy, and sometimes we call it traveling waves. It's energy. It's a traveling wave. Most probably signal is a wave because it has to travel, right? And it's electromagnetic wave. And the energy, it's not just a random energy. Right? Maybe it is. Maybe it's a noise, right? But no matter what, right? The energy that actually carries, okay, some sort of information. Even noise contains certain information. Maybe the information is useless, but it is a certain type of information. And we usually also describe the signal. Okay, we describe it, okay, as a function of time. Okay. Not always. This is more. I'm talking about more of a real-time continuous signal. If you have a discrete signal, it's not about time, right? It's about numbers. Okay. And in real life, signal basically it's a function of time. As time changes, the signal most probably will also change. So now back to the definition here is in real world. Okay, in real world, signals are continuous. So if you think about a thing, what you hear, if you think about anything that carries an energy in real world, they're all continuous. The chirping of the birds, the lights emitting from the bulb, right? The sound from some person, right? The computer that you're playing the monitor display, right? They're actually, whatever you see, right? Whatever you hear, whatever you observe in real world, they are all continuous. However, okay, in a digital world, which is what human beings interfering the natural world, we created discrete signal. Right? So it can be discrete in digital world. A digital world is not a natural world. It's a man-made phenomenon. And you have a computer. The computer will digitize the signal. The CPU will process the digitized or discretized signal. And after certain presentation, after certain processing, it presents back to you, right, with an analog or what we call continuous signal. So that's a difference, okay? Now, in terms of writing, let's say if you write x of t, this is most probably you're writing this as a continuous signal, right? For example, cosine t, right? So this is a continuous one. Right? Now, for discrete one, you maybe end up with writing x of n, and then cosine nk, or just cosine n, for example, right? Yeah. So n at here equal to 0, 1, 2. So when you plug 0, 1, 2 into here, what you get out of this is a sequence of numbers. That's what we call a discrete thing. So you will have much more opportunity, especially in electrical. There's a dedicated course on digital signal processing. Right? So you will deal with all of this, okay, in your third year. Okay. So now you know what the signals are. Okay. So what exactly can we classify a signal? I mean, we're going to come back to signal a little bit more here. Okay. Yeah. So now let's look at the definition of a system. Okay. So what is system? So here's the formal definition. Okay. So a system is any physical set of a component any physical set of components that takes signals, okay, maybe one or two, not just taking signal, but also produce signal. So this should be more of a very laid language in terms of describing a system. And if you think about it, any set of a component, right? I'll give you a few examples. So basically, it can be a set of a mechanical component, can be a set of an electrical component, can be a set of a civil structure, which is also a component, or maybe a mixture, right, of all different type of components. But the important thing is the system has to be able to take signal, which is what we call input, and it also be able to produce signal, which is what we call output. Right? So that is a system. If you see a black box, doesn't take anything, doesn't produce anything, that's a black hole, maybe, probably, right? So that's probably what we shouldn't call it a system. Right? So let's give you a couple examples here how you can actually classify, how you can draw the system when you're presented with a certain diagram. I'll give you an electrical system first. So what I draw here is a RLC circuit. And then you have your input over here. Let's call it VI. So you're given AC alternative currents input. And then the idea here is you want to measure the output across the capacitor. So that is a system. And when you try to clarify this system, right? So you can think about it from the input-output perspective. So you could also draw basically a black box. You know, your black box will be more or less look like this. So this box contains the RLC. Of course, now I already draw the RLC, but you may be presented with a box which contains the RLC. You might not be able to see through the box, right? All you see outside the box, you have an input, and then you have an output at here. Okay. So one of the ideas if you have the system given, how do I characterize the dynamics of the system? Basically, given this input, what will be the response of the system, the output? And if you change the input, how will the output change itself? Right? So the input-output, there's got to be a relationship, and that's actually one of the things that we will strive to get. Without going into details, the output and input relationship, what you will see is described by a so-called second-order ordinary differential equation. And we will certainly look at this in more detail later. So this is called a second order because there is a second order derivative at here. And this equation at here, you can clearly see involves both of the input and the output at here. So that connects the input-output using one math equation. And we'll be able to solve this one. Okay, we'll be able to solve this to give us a solution for the output, which will be a function of the input. So that's actually part of the course, is how do we get this solution, okay, based on a different type of differential equation. First order, second order. Right. Okay. So we'll get this back in details later. Right. So that's an electrical system. Right. You can certainly have another system here. So let's take a look at one more system. Let's call it mass damper system. This is very, very commonly seen in mechanical or civil. Okay, this is called a mass damper system. So let me ask you, had any of you have had experience with this so-called mass damper system? Okay, not really? That's fine. So we have one lecture actually to talk about how do we model this mass damper system. Maybe the question here, have you learned like these kind of RLC circuits in your first year? Yeah? Good, right? So then I don't need to go into the details when it comes to the lecture. So this is called a mass damper system. This is a spring. There's actually, I forgot to mention, mass spring damper system. Okay. So there's three components, three simple components in the system: the mass, the spring, and this is called the damper. Okay. A simple analogy I can use is, you see the door, right, of the classroom. You see the hinge of the door there. Okay, when you open the door and you let it go, it doesn't close immediately, right? It slowly closes off. So that hinge is basically the damper. And the door hinge, there's actually a spring on it. That's how the door can come back to itself. The door itself is the mass. Okay, so that's a simple system. If you want to understand using the door classroom. So this is a damper, this is spring, and this is a mass. So we'll come back later as to how you model this later, how to derive this. But the point here is you are interested basically in the motion of the mass when you apply an external force to the mass. Any type of external force. You apply to the mass, and then you want to understand how the mass, maybe you apply momentarily, then you let it go, or you apply it continuously as a sinusoidal signal, for example, right? And then you want to know how this mass, right, will behave given a time history. And we will be able to learn how to derive this, but the end results you end up with is mx double dot plus bx dot plus kx equal to f of t. And this is another second order linear ordinary differential equation. And inside this equation right here, you can clearly say it contains x of t. It contains y of t. So maybe I'll ask you the first question. A simple question. I think I already said it. Yes. What is the input to the system? The force, f of t. What is the output of the system? Yes, right? So for this simple system, you're not going to have a very complicated system. From this stage on, right, I need you to be able to always think from input-output perspective, not just a pure mass equation, okay? Yeah, you know, y equal to ax plus y is a straight line, it's pure mass. But we need to think from input and output perspective. Okay. So I see somebody raise their hands. Do you still have a question or no? You figured out? Okay, good. Thank you. Okay. I mean, the point here is I want you to get some idea of a relationship between input and output, right? Relation between signals and system, and how the relationship can be described without getting into too much details, right? And by the way, if you look at the writing in here, I think I mentioned in my first lecture, when I use a variable with a double dot on it, right, that's what we call Newton's notation. We apply Newton's notation a lot more often when the function is a time function, right? Of course, you can certainly use Newton's notation over here too. Okay? So just another illustration, I might have a mixture of different writings, you know, in terms of the derivatives. Okay. Good? All right, so the next question is, okay, you probably will also hear is a model. Okay, so sometimes you hear a key buzzword model or a model of the system. Yeah. So model, okay, to put it simply, it's a mathematical equation. Okay, it's a mathematical equation. Or maybe not just one equation. Maybe it's a set. So basically, there are a few more equations working together, especially when you have a multi-input, multi-output system. Okay. So there might be a set of equations. So what the equations, the purpose of the equation or equations is to describe, or even you can call it predict, okay, the behavior of the system. Okay. And that's basically how really that makes the human beings smarter than most other creatures in the world, right? So we are able to summarize, to derive abstract equations to actually represent the more complicated natural behavior, right? So the behavior here, right, in other words, right, is what we call dynamics. This one you have heard, right? You have heard statics and dynamics. So basically, behavior is not static. Behavior is a constant changing quantity, and that gives you the so-called dynamics. And that's actually part of the keywords in the course name, system dynamics, right, or system behavior. Okay, so this is more or less, right, the summarizing some of the basic concept here. The following is more to give you a bigger picture now, okay, without getting into detail, which we will in the near future. is that how can we classify the system? How can we basically present the properties of the system, or the categories of the system? Right? So now let's look at the so-called classification. The classification system. And also really top of the line, bigger picture, what we call properties of a system. Okay, so let's look at this bigger picture first, and we will dive into the details and how to determine, right, each one of these here. Okay. So first, let's look at how we will describe the properties of a system. Properties. How many properties we will use, right, for this class, for this course, or for the system? So for properties, there are three. Okay, there are three properties. The first property is called causality. And I'll explain this a little bit, what this means. Of course, you know exactly the wording. The second one is called linearity. And third one is to look at time invariance property. Time invariance or time variance, actually. Okay, so essentially, we'll look at that. So what is causality, what is linearity, and what is time invariance? And it's a really bigger picture. We will dedicate lectures on each one of these. Okay, and as a matter of fact, I will see a little bit about causality, maybe if you've got time for today. Okay. Now, based on the property, then we'll be able to classify. We'll be able to classify the system based on the property. So you have three properties, and you look at each one of the property, and then you try to nail your system right into each one of the actual property. For example, you look at the causality of the system. Is it a causal? Is it a causal system, or is it a what? So-called now basically the other way around, a non-causal system. Okay. So that's a classification. It's either yes or no. There's no ambiguity in between. So the meaning of the causal, I'll show you this a little bit here. Okay, just give me a few minutes. And then you look at the linearity, the second property, and then the question basically you can ask is the system linear or nonlinear? Okay, so. And I'll come to the definition of linear and nonlinear. And the last one is the system time variant or time invariant. Three classifications based on the properties, and all of them are yes and no kind of answer, right? So if you're given a system, you will see the exercise to determine the property or determine the classification properly. So let's look at the first one, causality system. Okay, so property, causality. When we talk about causality of the system, and I need to actually present a causality for the signal first. Okay, so signal causality. So this has nothing to do with the system causality. Okay, this is just a definition of a signal causality because we need that in the near future. Okay. So signal causality. Here's the proper definition. Okay. So causal. So let's call it causal signal. Okay. Signal can be non-causal, can be causal, very much like the classification of a system. If you have a causal signal, okay, it's causal signals. What are they? So they are the kind of signals, okay, that are 0 for all negative time. Okay, it's very, very simple. Negative time means when t is less than 0. So basically, mathematically, you could write it f of t is 0 for t less than 0. If you have a signal like this, then it's a causal signal. If you have a signal not like this, then it's a non-causal signal. Okay? So that's simple. So if I draw, for example, if I draw a signal here, f of t, then there, this is f of t. Do you think this is a causal or non-causal signal? Here's 0. Causal, right? So this is a causal signal. However, if you have a signal, okay, let's say there is a, sorry, actually, no, this is not accurate. So, okay, right? Something like this. There's non-zero part when t is less than 0. Then this is a non-causal signal. Okay? Yeah. I'll stop here, and then we'll look at the system causality definition in the next lecture. Okay, thank you.